Yes, welcome everyone for our new session of the row. Today we have two speakers, so I'm happy to introduce the first speaker, who's Zhao Kang. He completed his PhD at Eindhoven University of Technology, and now he's an incoming senior research scientist at Huawei. In his research, he focused on robust optimization, especially for inventory management, and also received already the Best Student Paper Award from POMS Supply Chain Management College. I'm very happy to have you here, and please, so.
So let me start. So good afternoon, everyone. My research topic is robust spare parts inventory management. So maybe some of you don't know what is spare part. Therefore, today in my story, we will start from this background figure. As you can see, the part I colored in yellow, it is a component, we call it cross pipe. In the early of last year, there was an earthquake happened in Taiwan, and some cross pipe were damaged due to this earthquake, which leads to the breakdown of the machines at TSMC. Also, it leads to the cost up to $16 million in 6 hours. So a very short time, but a very high cost. In this case, what we can do? The reliability engineer will do the replacement of the broken cross pipe with a new one. Therefore, the availability of the spare part will hugely influence the corresponding cost and the downtime. The cross pipe is only one component of this type of machine, and we call this machine extreme ultraviolet lithography machine. This machine is introduced by ASML in 2019 to produce chips for electronics. And for one of these machines, it includes more than 3,000 types of components, and the highest cost is higher than 1 million euro. In order to keep a very good performance for this spare parts inventory, ASML set up global warehouses around the world for their top 3 customers, Samsung, TSMC, and Intel. And they helped achieve that 99% of the demand can be fulfilled in 24 hours. In our research, we're focusing on one of these local warehouses, and we consider multiple components. We also call them stock keeping units, SKUs. And we consider a continuous review one-for-one based on policy. It means that once we have a broken spare parts from the customer, we will send the broken one directly to the repair shop, and the customer will get a new one from the warehouse. And after the lead time, the broken one will be repaired as a new one and sent back to the warehouse again. And we consider the aggregate fill rate as the main service performance. The aggregate fill rate can be understood as the total fraction of the demand can be fulfilled from stock immediately. Here, we consider a big challenge is during the new product introduction stage. At this stage, usually the demand data we have is very limited. Here we have first example from the air industry from British Royal Air Force. You can see that it is true that for some of their components, the demand is low, but the average demand is still around 20 or so. However, in our case for ASML, you can see that around 80% of the components demand is less or equal to 3, and the mean value is only 4 per year. But even though the demand data is limited, when we're making decisions about stock level, we still need to take into the consideration of the potential failure in the future, and also to do the trade-off between the cost and service performance. For conventional spare parts inventory, usually we'll assume that demand is Poisson or follow a specific distribution. And also some people, they use the Bayesian methods. However, this approach is very sensitive to the selection of the price distribution, especially when we have very limited demand data. At the same time, only few papers are really focusing on the new product introduction phase. Therefore, that's the reason we want to introduce robust optimization in spare parts inventory at NPI. And in previous research, there are still some research really focusing on the inventory problem, but for our problem, it is much more like a service performance-oriented problem. due to the spare parts inventory. And also we consider a continuous review based on policy. And for most of the previous research, they're focusing on the periodic review. For these researchers, usually they lack of the empirical evidence. So they do the test by the numerical experiment, but there's lack of the evidence to show the advantages of application of robust optimization. Besides, for large-scale ARO problem, usually it is hard to be solved. And that is also the reason why we have this research. So our research question is, what is a robust spare parts inventory control that performs well in case of the demand uncertainty? In order to answer this question, we start from the robust optimization model formulation and also to do the construction of the uncertainty set. Then we consider to solve it, therefore we consider the reformulation and algorithms for large-scale ARO problem. In order to evaluate the performance of our robust model, here we conduct a series of simulation-based experiment and ASML case study. Now I will go to the basic concept of our model. At the first stage, before the realization of the demand, the supply chain planner will make the decision of stock levels, SI. And then the demand can be realized. After that, we can make the second stage decision. That is the fill rate we want to achieve. You can also consider it as an auxiliary variable. We consider the adaptive robust optimization approach here. Therefore, we consider the stock level as the first stage variable and the fill rate as the second stage variable. This is how our model looks like. The object function aims to minimize the total inventory cost, which is the summation of price of SKUs times the stock level. And the first constraint guarantees that for each individual SKU, the stock level SI should be higher or equal to the fraction of demand we want to fulfill from stock directly. And the second constraint is for the aggregate fill rate. Here you can see we have beta OBG. Usually should be higher or equal to 0.9. It means that 90% of the demand should be fulfilled from stock immediately. And based on the definition of fill rate, we have the third constraint. You can say for this type of model, usually it is hard to be solved directly because the beta I is a function of zeta demand, and it is also multiplied by the zeta I. Therefore, in order to solve it, we show that the ARO problem can be reformulated as a deterministic robust counterpart. And now the model can be solved because the constraints here are the typical linear constraints with right-hand side uncertainty. Here, we also have an example when we have 3 SKUs, how the constraint looks like. So you will have individual for the constraint S1, S2, S3, and also you have any combinations of the stock levels for these SKUs. Here, you can see a big shortcoming of this type of reformulation is the number of constraints will increasing exponentially with the number of SKUs we have. Therefore, in order to solve it, we introduce our first algorithm. We call it IPDO. Now I will use an example of 3 SKUs to show the idea of IPDO. The first SKU we consider the most expensive one, and the last one we consider the most cheap one. And we're first to reformulate the coefficient of the constraint in this type of matrix. For instance, for the number 4 constraint, it means S1 plus S2 should be higher or equal to 8. Now let's start to use the IPDO to solve this type of problem. We started from the most expensive one, and we hope to stock it as less as possible. Therefore, firstly, we only consider the constraints only including the first SKU. That is the first constraint of this matrix. So then we can find what is the minimum B we have for this constraint considered. That is 4. So the stock level of the first SKU is 4. Now we go to the second SKU and we consider the constraints including both the first SKU and second SKU. And now, given the stock level of the first SKU, we can then calculate what is the new B we have for the constraints including the second SKU. And also we can find out what is the minimal B of this coefficient we considered. And that is 4 also. Using the same idea, we go to the third SQ to consider the constraints including both first SQ, second one, and the third SQ. And also, we can calculate the B-value again, given the stock level of the first two SQs. And that is still 4 here. And we find that IPDO has an entirely different way to approaching solutions compared to the greedy algorithm of the stochastic model for spare part inventory. Because for IPDO, we usually give the advantage, give the advantage for the expensive SQ first, and we hope to stock as less as possible for expensive one. Well, for greedy algorithm, typically it will give the more advantage or privilege for the cheap SQs, and it helps to stock for cheap SQs as more as possible. And we also show that IPDO can give us optimal solutions when there's no any redundant constraints. However, in practice, we do find there's a lot of constraints are redundant when we're using different types of uncertainty set. Therefore, we have a simplified version. We call it constraint generation algorithm. For this algorithm, we only consider a part of the constraints, not all of them. We then do the comparison of our algorithms with some existing methods. For instance, we can solve to find out the exact solutions by several grouping. And also, we used two commonly used approximations in robust optimization, the affine decision rule approach and static approximation approach. Now, let's see the performance. We start from the testing of the computational time. It is clear that when we increase in the number of SQs, the server grouping first stop working due to the memory error. And then for both of the approximation methods, they stop working also for the same reason. However, for our methods, especially for the IPDO, their computation time is very small and it can go to hundreds of SQs. Now, let's see the error of these algorithms. We compared the MAP values of the stock levels. It's clear that when we're increasing the number of SQs, for both of the approximation methods, the error will increase very quickly. But however, for our algorithms, they still can achieve the optimality. So now we have algorithms, we have the model. Another thing we need to consider is how to build up the robust uncertainty set. In today's presentation, I only show two types of uncertainty sets. The first one is the most simple one, we call it box, because it only considers the upper bound and lower bound of each demand. We also consider the most complex one, we call it extended budget uncertainty set. In this case, you can say not only we consider the individual bound for each of the demand for each SKU, we also consider what is the combinations for each of these SKU, what is their upper bound and total and lower bound. And we help to use this way to capture the interaction of these demands in our case. Now, let's go to the numerical experiment. We started from an illustrative example of non-SQs. For these non-SQs, we consider different collaboration of the combination of their demand rate MI and their price CIA. And therefore, we will have these types of metrics to say, given different demand rate and prices, how the stock level of these components will be. And for each of them, we will increase in the target fill rate from 0.1 to 0.9. It is clear that for most of the expensive SQs, robust one will have higher stock levels than the stochastic model when we're increasing the target fill rate. And for most of the cheap SQs, the greedy algorithm of the stochastic model will usually stock more. And we also find that for the same class of the demand rate, usually the increase of the stock levels for robust model will show similar trend. Therefore, we conclude that for the stochastic optimization model, it prefers to stock more for cheap SQs, cheap spare parts. However, for robust model, because it takes into the consideration of the worst case of the demand, so it is much more focusing on the worst case scenarios of demand, and it is much more like a demand-oriented solution. Finally, I want to go to the ASML case study. We consider 710 SQs. For these SQs, we used first 2 years data to generate solutions and the final year data to test their performance. And we compared our robust model with the stochastic model because this is one very typically used at ASML and other companies in industry. And for the stochastic model here, we consider the Poisson demand and greedy algorithms to solve it, and we call it SPAR10. For robust model, here we consider the constraint generation algorithms to solve it. And firstly, we want to see what is the cost efficiency trend for both of the stochastic model and robust model. Here we set up the target fill rate from 85% to 99%. It is clear that for the conventional stochastic optimization model, for instance, when we set up the target fill rate is 99, it's actually similar fill rate can only achieve around 82 or 83. So it means that the actual performance of the stochastic model is far from the target we want to achieve. However, you can see the points we colored in red. They are the solutions of robust model. You can see for most of the cases, they can meet the target fill rate. And now let's make this picture more clear. You do can see there's a gap between the stochastic optimization model and robust model. And we found that when we use the robust optimization model, we can save up to 15% on the cost. Now let's answer our research question. In order to find out what is a robust spare parts inventory control that performs well in case of the demand uncertainty, we first propose a robust optimization approach to spare parts inventory management, especially during the NPI stage. In order to solve it, we show how to reformulate the RO problem to a static robust model. And also then, we show two different types of algorithms, and we proved the optimality of one, we call it IPDO. We conduct a series of numerical experiments to show how the performance of our ARO model, and also our ASML case study shows that our RO model can save up to 15% on cost. So that is all of my today's presentation. Thank you all.